to review what we talked about last week, right? We started talking about heat. Okay, we started talking about heat and the transfer of heat. So what I had you guys do was like touch the top of your desk and touch like the metal part of your desk, and one felt warmer, one felt colder, correct? Okay, we gave those two terms. Okay, one of those terms was called an insulator. All right, insulator. It absorbs heat really well. Oh my gosh, I'm drawing a blank. Insulator. What did I just say? Conductor. Thank you. Oh my gosh, it's Monday. Insulator and conductor. All right, and this conducts heat really well. It releases heat. Releases heat really well. Okay. So on Friday, I gave you 2 blocks. Do you guys remember that? Gave you 2 blocks. You don't remember the 2 blocks? That's so sad. I didn't give you these 2 black blocks. I can't believe that. Okay. Well, what I want you guys to do. Okay, we'll go to like start to plan A. What I want you guys to do is find a partner or like a group of 2 or 3, whatever you guys want, and come up and grab these blocks. Let's start with that then. Okay, come up, grab a pair of blocks, and then I'll tell you what to do with them. Should have enough. Just one per group? Yeah. So one of the blocks is made out of aluminum, the other block is made out of foam. The aluminum is a conductor because it releases a lot of heat, whereas the foam is a good insulator. It feels really warm, where this feels really cold because it conducts heat. All right, so ladies and gentlemen, what I want you guys to do is make sure your phones are away. 1, 2. I want you guys to feel both of them. Okay, feel both of them. All right. Feel both of them. Okay. Now, which one? All right. Let's say this one, the one that kind of sounds like that, right? That's aluminum. We're going to call that aluminum. The other one kind of sounds like that. You probably know it. That's just foam. Which one feels cold? The aluminum. The aluminum feels colder, correct? Feels cold on our hands. So, how is heat transferred with my aluminum block? Yes.
It releases faster.
Heat is released from the aluminum?
I mean, when you come in contact with it, it releases faster.
How is heat transferred though?
From your hand.
From my hand to the aluminum?
Yeah.
So my hand is hotter.
Yeah.
So the block is colder. You're exactly correct. All right. So my hand transfers heat to the block. Now, we said the aluminum is colder. Is that true?
Yeah. Yeah.
Do you think I put this in like the refrigerator? So this is at room temperature. Then what's this at? So they're both at room temperature. So they have the same temperature. Why, if they have the same temperature, why does it feel colder? Metal? What's the metal? What's the system about that? They're conductors, so they conduct heat. So they have different transfers of heat. Okay? Now, a little interesting. Now, what I want you guys to do is set each block out side by side. Okay, side by side. Get out those two little rings you have. Okay. Okay. Everybody got that? Put it on the blocks. Put 2 rings on the blocks. And what we're about to do is we're going to put some ice on this. I'm going to put some ice on both of them. Now, you don't have to write anything down, but I do want you to make observations. I do want you to make observations. So you don't need a lot. Honestly, like just a chunk and a chunk will do good. Okay? Put them on at the same time and watch what happens. Okay, so that you guys can see what's happening. Okay. So I put them on at the exact same time. As you can see, the second one is actually already melting, where the first one hasn't melted at all. See how quickly that's melting? And that one hasn't even melted at all. Okay.
Hey, we don't have to turn anything on this time, so then it just melts.
Okay. So, hopefully everybody was able to get ice on both of them. If you need paper towels, I got paper towels everywhere. Okay. Now, we said aluminum. Okay. So real quick.
Too late.
That's okay. So guys, listen up. We said aluminum felt colder, is that correct? Okay, so aluminum feels cold. Which one melted the ice more? The aluminum. Okay. So, when checking this out, guys, listen up. Gentlemen, so we said aluminum felt cold, but it melted the ice. So this felt warmer. If this felt warmer, why didn't that melt the ice faster?
Because since it's a conductor, it releases more heat, causing for the more heat to melt it faster.
You're exactly right. All right, so a conductor, it transfers heat. Now, when we felt it in our hand, oh, that's going to be terrible. Thumb, finger. There we go. When we felt it in the hand, the heat traveled from our hand to the block. But now, when the block has an ice cube on top of it, now the block is actually transferring heat into the cube. Pretty crazy. Now, can anybody think of a way we could have sped that up a little bit even faster? Silas?
heat it up to the thing before we put it on there.
Heat up the aluminum? Absolutely. How could we do that?
With a torch.
Okay, we could use a torch. What's a simple way though? I don't usually carry around torches. Sometimes I do, but yeah, Matthew. Put it on your hand. What if we put it on our hand like this? Right? Then heat would travel to the block, heat up the block, and that would melt the ice even faster. Pretty crazy, right? Pretty crazy. So hopefully this was a decent visualization. Wherever you guys have your blocks, you guys can just leave them there. But look at the foam. Holy smokes, mine just, I think, started to get a little watery at the bottom. I don't know about yours, but just a little bit. All right. So I've got a little video I want to show you guys real quick. So we can come back to our desks. All right. Okay. Okay. So this guy does a very, very similar experiment to what we just saw. All right. Just a really good, I like this guy. He creates good videos. The Vertasium guy. You guys remember Vertasium? He was the Chernobyl guy. Creates really good videos. It's just 358. So let's watch this real quick.
Object and it feels warm or cold, what is that really telling you about the object? Here I have a metal hard drive and a book, and I'm going to ask people to compare their temperatures. Which one do you think will feel warmer, the book or the hard drive? The temperatures? Yeah, tell me if one is hotter or colder, or if they're the same temperature. How do they feel?
This is slightly cooler than this one.
Yeah, that's warmer. Yeah, like.
Yeah, agreed.
I'd say the hard drive is a lot colder than the book. I don't know, because the book's got more knowledge.
Why do you think that is?
Metal's normally a little bit chillier if you leave it in a colder temperature.
Well, what if I said that they're both at the same temperature? What would you say? So you're lying. Really?
I think you're lying, yeah.
Oh, geez. Well, maybe the way I can prove it is I have an infrared thermometer. What do you think we're going to see?
I think science might be able to answer that. I don't know the scientist.
Make a prediction for me.
I still think that's cool.
Would you bet me money?
I don't, because I don't have any cash for it.
Let's measure the temperature of the book.
Okay.
What do you see?
19.0.
Okay. And measure the temperature of that.
19.0. Alright, well now I believe you.
I'm trying to actually figure it out, actually. Trying to figure out why they would be the same temperature. They don't feel the same temperature, though.
So why does that feel colder if they're basically the same temperature? Good on. You get an answer? Well, I'm coming to you guys for answers.
So like creatives, not intellectuals.
Well, create an answer for me.
I'm not a scientist, come on, you tell me.
Well, I'll try to answer that question with another little experiment. Here is an aluminium block. And
Ooh, nice and cool.
a plastic block. How do their temperatures compare?
Completely different. Completely different.
Aluminium much colder.
Yeah.
Yeah?
So this actually feels colder.
Let's take this to the next level. I'm going to put an ice cube on both plates. What are we going to see?
Well, I'm guessing it would stay solid on this one and melt on this one.
So it's going to melt on the plastic but stay solid on the aluminium.
Yes, but maybe I'm wrong.
That one will melt more quickly than on the aluminium block.
Yes. And the colder.
Yeah, because it's colder.
Let's
I
actually.
think they're going to go the same.
All right. So we put an ice cube on each of those blocks. What do you see?
Well, it is melting a lot quicker on the aluminium.
I got it melting.
It's not even than that one. Even though this is aluminium, that's plastic.
So which one felt colder?
That
This
one,
one.
How does that make any sense?
I have no idea. Will aluminium be bad for the environment?
How would aluminium be bad for the environment?
Well, it's thawing out the ice a lot quicker, isn't it?
So you want the answer?
Yes, please.
It's about thermal conductivity, right? The rate at which heat is transferred from one object to another. So when you felt these blocks originally, I know this one felt a lot colder.
Yeah.
But you know from the other example we did that they must both be at the same temperature because they've both been outside for a while. We see that the aluminium block is melting the ice faster than the plastic block because it's conducting the heat to the ice cube faster.
Okay.
With the plastic block, it's a worse thermal conductor. So heat is being transferred less quickly to this ice block, and so it's staying ice.
Okay, I believe you.
Make sense?
Yes, definitely.
You know, in our first example, the hard drive felt colder even though it was at the same temperature roughly as the book. And that's because the aluminium conducts heat away from your hand faster than the book conducts heat away from your hand.
Sure, that seems logical.
Which makes the hard drive feel colder and the book feel warmer. So when you touch something, you don't actually feel temperature. You feel the rate at which heat is conducted either towards or away from you. Think about this next time you hop out of the shower in winter. It's much nicer to stand on the bath mat than on the tile beside it. Not because the bath mat is warmer, but because it conducts heat less quickly away from you.
Pretty crazy to think about. Wasn't that pretty crazy, Landon?
Yeah.
Yeah, absolutely. Pretty crazy to think about. Crazy. Fact light's coming on. 3, 2, 1. All right. So, how do we feel on heat? Transfer of heat. We feel pretty good on that concept?
Yeah.
Okay. Now, we're going to learn about one term today. And one term, it's called specific heat. What is a specific heat? Okay. We're going to focus in on that. Every substance has a different specific heat. The aluminium, I like how they say that, honestly. The aluminum has a specific heat. Water has a specific heat. Everything has a specific heat. All right. So let's introduce what in the world specific heat is. Just got a few slides here. What is specific heat? All right. To start off, why is the sand on the beach hot, but the water is cool on the same hot day? All right, we know the transfer of heat, right? We already got that. We got that down. Okay, so how much heat is being transferred is what we're actually trying to solve here. Okay, that's what we're trying to solve. All right, they have different capacities to store it. Okay. Okay. So how much heat or how much energy, I should say, is the specific heat? Okay? All right. Now, this is the definition. Pretty good to know. Pretty good to know. The definition of specific heat is the amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. Ooh. It's a lot to think about. The temperature required to raise the temperature 1 degree Celsius, that weighs 1 gram. Okay? You might want to know that. Okay? Okay? And which is the same thing as the ability for a substance to absorb or release heat. Okay? Let you guys copy that down real quick. You will need a calculator today. Does anybody need a calculator? You're ready to go. Okay. See, the amount of heat required to raise 1 gram of a substance, 1 degree Celsius. Okay. So, the higher the heat, the more energy. All right. That makes sense. The higher the heat, the more energy. I'm going to erase this. This. Okay. So higher the specific heat, more energy. Okay. Let's look at a concept question. Aluminum has a specific heat of 0.9. That's its number, 0.9. Lead has a specific heat of 0.13. If equal masses of both metals are heated to 100 degrees Celsius, which is going to have more energy? If both have equal masses and are heated to the same temperature, which of these two numbers will be greater? Aluminum, right? Aluminum. The aluminum will store more energy. Pretty crazy. Okay. And there's a way to solve that. There's an equation we're going to use. Right? There's an equation we're going to use. And this is what it looks like. Might want to write this down. All right, so the heat gained or lost, that is Q. That is represented by Q. Heat is measured in joules. Okay. That is equal to the mass. We know mass. Specific heat, that's what we're talking about. Specific heat is represented by a capital C and a little lowercase p. Capital C, lowercase p. And here are the units for that. That is a lot. And then the last thing is the change in temperature. And they're all multiplied. So that makes it a little bit easier, knowing they're all multiplied by each other. Okay, so Q equals MCT. Q equals MCT. Okay. Okay. Now, one thing that you will become familiar with, it's a good number to know, is 4.18. Okay, that's the specific heat of water. We're going to do a lab tomorrow. You'll need that number. Okay, so the specific heat of water is 4.18 joules per gram Celsius. I would know this for tomorrow. It's pretty cool lab. Hopefully we get good data. Everybody good? All right, let's try one of these out. Okay. Oh, that's one. Okay. A temperature of a piece of copper with a mass of 95.4 grams warms from 25 degrees Celsius to 48 degrees Celsius when metal absorbs 849 joules of energy. What is the specific heat? What is the specific heat? So to start off, I would probably write out the equation. That's our equation, right? So when you check this out, what is the absorbed heat? How much heat is absorbed? $849. So the absorbed heat, 849, is equal to the mass. What's the mass? 95.4 times the specific heat. Do we know that? Okay, so times Cp times the change in temperature. Now, when you have change in temperature, what that is, it's the final minus initial temperature. Okay, change in temperature is final minus initial. Okay, so what's my final temperature? 48. So my final is 48 minus the initial was 25. So how much did it change? It increased 23. Does that part make sense? Bless you. Does that part kind of make sense? It increased 23. Now we should be able to solve. So you can, it's all multiplication, so you can divide 95.4 over 849. Okay, so I got 8.9 is equal to Cp times 23, and then you can divide the 23 over. Okay. I got my specific heat to equal 0.39. Okay. Now, what's its unit? Degrees Celsius. Perfect. So the specific heat is 0.39 times joules over grams degrees Celsius. Okay. Question. Try this one out. Hello. Hi. Yeah, I can do that. Sounds good. Yep. Right. Okay. Let's try this one out. Little tricky. but I believe it.
Mr. Bowers,
Yeah.
do you have Johnny Moreau in there?
No, he's absent.
Okay, thank you.
Yep. Man. I wonder how they do that. Like, what's the difference of a call from that? I don't know. Did anybody get an answer? Devin, what'd you get? 1,045. That's a big number. That's exactly correct. 1,045. All right. So if we check this out, what's the mass? 10. Perfect. Okay. Where does this is the specific heat in this problem? Is it right here?
No.
Anywhere? No.
Water.
But it's water. So water, hopefully we can get that number and plugged into our brain. 4.18, right? Right? That was from like one of the previous slides. Now, the change in temperature. Remember, that's final minus initial. So what's my final temperature? 55. Minus my initial temperature was 30. And when you plug that, wow, that one's right on the line there. That's 10. There we go. When you plug that into your calculator, you would get 1,045. Now,
Please excuse interruption. Johnny Moreau, would you come to the attendance office, please?
so you get 1,045. What's the unit? Joules. All right. Now, there are some things I want you to watch out for. Honestly, there's only mainly one. Make sure you watch out for units. Okay? That's in joules. Okay? Some problems will give it to you in kilojoules. Okay? Just to watch out. All right? So we know our metric prefixes. All right? So if you're going from, let's say, kilometers to meters, if you move 3 spots to the left, you're going to move your decimal 3 spots to the left. So this number is actually the same as 1.045 kilojoules. Watch out for that. Okay, just a heads up. Joules to kilojoules. Let's see, what else? Honestly, the same thing. Grams to kilograms. I would watch out for that one. Okay, other than that, we would be good. How do we feel, guys? All right, that is all I have for today. I don't think I had a third one. I think we're good. All right, you guys got about 4 or 5 minutes left. You guys have any questions?